Hey guys, welcome back to Quick Code. Today we're doing another Brainstellar Quant puzzle. This one is called Rainbow Hats. It's a medium problem. So there's a small correction in the wording of the problem. So I've changed it over here. Instead of first n natural numbers, it's first n whole numbers, as in from 0, 1, all the way up to n minus 1. So I'll pause right now. So, first of all, in my opinion, this is a tough problem. It was not easy. It took me quite some time to develop a somewhat intuitive explanation to this problem. So, first of all, let's explain the problem. So, let me take an example of n being equal to 5, right? So, what happens is, first of all, there's 5 people in a room and they discuss a strategy on how to play this game. And the game goes as follows. So, first, these 5 guys will discuss a strategy among themselves. Then they all walk into a room where they are all assigned hats. So let's just call them person A, B, C, D, and E, right? Now, once they get inside this room, they cannot talk to each other, and each of them is made to wear a hat. So let's say HA, HB, HC, and so on. And it is given to us in the problem that each of these values from HA all the way to HE, each of these values are going to belong from 0 to 4. Since it's mentioned in the problem, mentioned that on entering the room, each person is given a hat on which one of the first n whole numbers is written. One of the first n whole numbers, so let's say n is 5, then that means from 0 to n minus 1 would mean 0, 1, 2, 3, and 4. So each hat is going to have a number among this range over here, right? So we now know that HA to HE, each number is a value from 0 to 4. Each of one of them is assigned a hat. And of course, since they're wearing their own hat, so for example, for person A, he only knows the values HB, HC, HD, and HE. He does not know his own value. He does not, so A does not know the value of HA. A does know the values HB all the way to HE, but not HA. And similarly, B knows the value of B does not know the value of HB, but he knows the value of HA and HC all the way to HE. And the goal of this entire game is to ensure that at least one person among A to E, or in general among the N people that initially are present in the game, guesses their hat correctly. So we have to have at least one person guessing their own hat correctly. So that could be A guessing HA correctly, or B guessing HB correctly, and so forth, right? And to achieve this goal, we have to think of a strategy that each of the N people agree upon and follow by before they enter into the room and the hats are assigned, right? So, this is the thing that we have to come up with, a strategy which ensures that once they enter into the room and they have been assigned their hats, they can ensure that at least one of them guesses their own hat number correctly. And there are also other details mentioned in the problem. So, for example, there may be duplicate hat numbers, right? So, let me just take an example of assignments of the hat. So, let's say HA got 0, HB also got 0, HC got 1, HD got 1, and HE got 2, right? So, 0, 0, 1, 1, 2. This is a possible arrangement. Or let's say the n was equal to 3, then 202 is also a possible arrangement, right? So a naive approach could be to just for example, let's just have our strategy as each person. So we already know that there's 5 people, right? The people already know the amount of people that are present in the game, right? So just for example's sake, let's say 5, right? So let's say that each of those guys is gonna announce the number 4, right? So let's say A thinks he has had 4, B also 4, and likewise. Now the reason why this won't work is, let's say the distribution was 0, 0, 1, 1, and 2. So in this case, nobody has the hat number 4 and nobody is correct, right? So this is why this won't work. The reason they've mentioned that the hats can be duplicates ensures that it can't be the distribution 0, comma 1, comma 2, comma 3, comma 4. In which case, picking any number from 0 to 4 and making sure that everyone says that same number would ensure that at least one of them is guessing the correct number. But because the numbers can be duplicates, it could be 0 0 comma 2 comma 3 comma 4. And if by chance we make the strategy of everyone announcing the number 1, then nobody's going to be correct. And by this strategy we can't guarantee to always have one person guessing their own hat correctly. So this approach of picking a random number from 0 to n minus 1 and making sure that every single person announces that same number, let's say I, which is from 0 to n minus 1, does not ensure that this is always gonna guarantee one person to say their correct hat, because it could be so that nobody has the hat numbered I. So this is why this doesn't work. So now, hinting towards the proper solution, it's very important to understand that since we have n people and we only need one of them to be correct, don't need more than one person to be correct, right? We have n people, that means n guesses for their own hats, and we only need one of them to be correct. We can take advantage of this. How? Well, if we think of a function or an expression for that matter, which only has n different possible answers, there's only n possible answers within the range of answers that that expression or function can produce. And if we pre-assign each one of those distinct answers to each person, so there's n people, right? And let's say all the answers could be 1, 2, 3, 4, and 5. Now, if I assign each answer to a person, so let's say person 1 is assigned the answer 1, person 2 is assigned the answer 3, and so on, then this guarantees that no matter what's the actual answer of this expression, we already know that it's going to be somewhere between this. And since each one of them is assigned one of the possible answers, this guarantees that at least one of these 5 people, or in fact exactly one person among these 5 people, or exactly one guess among these 5 guesses, is going to be correct. It's crucial to understand this point. What we're trying to do is trying to think of a function or an expression which has only n different possible answers, and we're going to assign each of these n different answers to the n people, ensuring that at least and exactly one of those n people is going to be assuming the correct answer. So, okay, so we think of an expression which has only n different possible answers, and we pre-assign each of those n people to assume one distinct possible answer. And this ensures that one of them is going to end up assuming the correct answer. Now, having said all this, one function that comes to my mind instantly is modulo, and to be exact, modulo n. So any expression, any integer value expression, modulo n is always going to give an answer from 0 to all the way up to n minus 1, right? 0, 1, comma 2, comma all the way up to n minus 1. Any value modulo n, given this is a proper integer value or expression, when we modulo it with n, the answer is always from 0 all the way up to n minus 1. And so we're going to use an expression including modulo n to ensure that the answer is always going to be within this range. And what we're going to do is assign each one of these possible answers to a distinct person. However, we still haven't addressed the exact expression itself, right? So we first need to think of an expression that includes the hat values, includes HIs, where I is basically a template for all the different people from 0 all the way to n minus 1, and HI is the value PI or person I got, right? So we need to think of an expression that includes the value hi. Why? Because this is the value that we need to guess ultimately, right? So if we create an expression, assume these answers, give each particular person an answer, ensuring that at least one of those guys is assuming the correct answer, and using the correct answer, if he tries to backtrack the value of h of I, he is going to get the correct value of h of I. And all the other guys who assumed the wrong answer for this expression are gonna end up backtracking wrong h of i's. But that doesn't matter, because the one person who's gonna assume the correct value of the expression modulo n is gonna backtrack to the correct value of h of I, and that guy is gonna announce h of I, meaning he's gonna announce his own correct hat value. And in fact, h of I should be the only unknown value among this expression, because we're assuming that this guy knows the correct answer to this expression and he's backtracking the value of h of I. That anything else within this expression has to be already known to at least that person. All of this will become more and more clear when we start talking about the actual solution. Right now, I'm just trying to hint you guys towards the proper solution. So let's also assign a few variables in order to denote everything clearly. So let the people be as follows, right? Since we've got n people in total, we can assign each one of them a value of p0 all the way to pn minus 1. This is just to denote each individual person. Now, we could also assign the hat values that each person gets as h0, h1, all the way up to h of n minus 1. All this means is n0 denotes the hat value that p0 is assigned eventually. Right? Now, let's also denote a variable called a as the total sum of all these hat values from 0 to n minus 1, which would look something like this. Right? This basically means a is the sum of all these values from h0 to h of n minus 1. Let's also assign another thing called v0, v1, all the way up to v of n minus 1, where basically vi denotes the sum of all hats visible to pi. And this would actually mean that vi would come out to be a, which is the sum of all the hats that are present minus hi. Why? Because vi can see every single hat except his own hat, right? Sorry, pi, person I, can see each and every hat which is within a except his own hat hi. So vi becomes the sum of all the hats that are visible to pi, which would be all the hats possible minus the one hat that is not visible to pi himself, which would have a value of hi. So vi becomes a minus hi for each pi. So first of all, we're gonna let every person be assigned, assume an answer to the expression a modulo n. Right? So this is the expression we're gonna use, and a modulo n will actually, for from each person's perspective, be vi plus hi modulo n, right? So, for example, we're going to assume that p0, or we're going to assign p0 to assume the value of this expression to be 0, and p1 to be assigned to assume the value of this expression to be 1, and so on for p n minus 1, assuming the answer to be n minus 1. Now, it's important to understand what exactly are we doing over here. This is going to be an expression which has a constant value, right? Because once the hats are allotted, there's gonna be a certain value of a, right? There has to be. And on moduloing it with n, we are ensuring that whatever this value actually is, it is going to be a value from 0 to all the way to n minus 1. This cannot map to any value outside of this range of 0 to n minus 1. And for each person to assume the values from 0 to n minus 1 ensures that at least and exactly one person, there's going to be a person pi dash. I dash is the lucky one who assumes the correct answer to this expression, right? There's going to be one value among all these n people. Let's call him pi dash, who is going to assume the correct value I dash, which is the actual answer of a modulo n. So again, a modulo n is going to end up being some value from 0 to n minus 1. And since we're assigning each of the answers to the n people, there's going to be one person p dash who's going to assume the answer I dash, which is going to be the actual solution of the expression a modulo n. So now, from each person's perspective, since he assumes I to be equal to a modulo n, and a could be substituted as vi plus hi modulo n. Now, looking at this expression over here, it's important to understand that from PI's perspective, this is what is correct, right? Of course, for each I from 0 to n minus 1, there's actually just one guy, I dash, who is actually assuming the correct value of I. But nonetheless, everyone's gonna think along the same lines. So again, yeah. So now each person has assumed a value of I. Each person knows the value of n. Each person does not know the value of hi, his own hi, but each person does know the value of his own vi, right? So he's gonna plug in the values of vi, n, and I, and backtrack towards the solution of hi. So this means that from each person's POV, he's gonna conclude a probable value of hi, which just means that each PI now has a guess for the value of HI, a guess for the value of the hat he himself is wearing. Right? And among all these PI that are guess HI, the person PI dash, since his I value was correct for the expression modular, he is going to end up guessing the correct value of HI dash, right? Now, why is this? Because pi dash just assumes by chance the correct value of a modulo n, right? So this expression is in reality true, right? He definitely knows vi dash, right? All he just needs is hi dash, and that's the only unknown, right? So hi dash that's gonna backtrack out of this equation is gonna be the actual hi dash, right? So this just proves that pi dash is gonna deduce the real value of hi dash. Since everyone was assuming their answers to be correct, everyone's gonna go through the same calculations, and all of them together in the end are gonna announce the value of hi that they have guessed out or calculated out. And among all of these guys, the person pi or pi dash rather is gonna be announcing the correct value of hi dash. Thus, we achieve the goal of at least one person, where in this case, exactly one person getting their own hat correctly. Again, in my opinion, this is a very difficult problem. So I recommend you guys to go and rewatch the video at 2x or something in order to really let the concept sink in. Hope you guys like this video and thanks for watching.